Now let's compute the posterior distribution. The posterior distribution for the mean of a univariate Gaussian. Univariate Gaussian. Whenever you're doing Bayesian inference, the posterior distribution, the probability of theta given the data, is always an essential thing to get your hands on. And so here we're gonna see how to compute this in this very simple special little case. So this is a cute little calculation if you haven't seen it before. All right, so as usual, we've got some data x1 to xn, and here the xi's are just real numbers. And we will model these data by some random variables x1, capital X1 through xn, that are distributed according to a normal distribution with mean mu and variance sigma squared. And we'll assume that they're independent, so they're IID, and they're independent given mu. And I emphasize given mu because we will model mu as a random variable, and it will also be normally distributed, and it will have mean mu naught, or mu 0, and variance sigma naught squared. Okay, so these are conditionally independent given the random variable mu. So we'll assume that sigma squared, this variance, mu naught, and sigma naught squared are all known. So we don't need to infer those. And so our parameter theta in this case is just going to be mu. Okay, and the parameter, note, is a random variable. So we put a distribution on it, so we're in Bayesian world. All right, now let's compute this posterior thing here, this posterior distribution. Well, it's posterior on theta. Theta is just mu, so we can just put probability of mu given the data. And this is going to be a density. We can see here. Well, it is going to be a density. It might not be totally obvious, but it should be pretty clear that it's going to be a density. And then, what is this? Well, we can use Bayes' rule. Probability of the data given mu times probability of mu divided by the probability of the data. That's just good old Bayes' rule. And this is proportional to, since this doesn't depend on mu, proportional to, maybe I could put like with respect to mu or something here, probability of data given mu times probability of mu. Okay, that's looking good. Now this part, what's this? Well, we are assuming that the data are independent given mu. So this becomes a product. Let's pull probability of mu out front here. We get the product as I goes from 1 to n of the probability of xi given mu. And let's go ahead and actually we're going to plug in the expressions for the normal. Now, since we've got this in a nice form that we have expressions for each of these quantities. So we're going to plug those in. And I'm going to use proportionality here because it turns out that the constant, so there's constants that we can just drop, because these things are all known. So this is proportional to e to the minus 1 over, let's see, so mu is, what's this one? So it's 1 over 2 sigma naught. Maybe I should put x. Let's make a new line. I think we might need a little more room. This is proportional to e to the minus 1 over 2 sigma naught squared. So we're looking at this guy. Mu minus mu naught squared. Just a one-dimensional Gaussian. And then we've got the product here. E to the minus 1 over, this one's sigma squared xi for the ith one, minus mu squared. All right, looking good. Now we can pull all this stuff together into the sum, make the exponent a sum. So let me just make sure, let's see. So I dropped the constants of proportionality, right, because it's just a sigma squared. There's a factor involving sigma squared and a factor involving sigma naught squared over here, but those are they do not depend on mu, on theta. So we can drop those out. They're just proportional with respect to mu. And let's pull together these exponents. So what are we going to get here? Let's see. We're going to get that thing, minus 1 over 2 sigma squared times the sum as I goes from 1 to n xi minus mu squared. Okay. So let's work with this exponent here. Let's just pull that out and work with that separately. Now what I'd like to do is so this let's see, how do I want to say this? This is, we're thinking of this as a distribution. It's proportional to a distribution over mu. So thinking about how this depends on mu, if you were to square out, if you were to multiply these out and collect terms, then you would see that in what you get, that you'll have a constant plus something times mu plus something times mu squared. So it's a quadratic in mu, and that means that it's going to be, if you know your probability distributions, it's going to be a Gaussian. This is going to be a Gaussian for mu. So let's see exactly explicitly how that happens. So we're going to look at this part, and I want to get this in a form. I want to get this in a form that looks like some constant plus another constant times mu minus some other constant m squared. This is going to be like the mean of the distribution, and this is going to go into the constant of proportionality, and this will tell us something about the variance. So let's see if we can do that. So we're going to pull this over here. This equals, how are we going to do this? Well, maybe we should just start by multiplying these things out and collect terms. Is that what we should do? Yeah, okay. This is just straightforward algebra, but I wanted you to see exactly how it's done. So actually, let's forget about the minus for now. Oh, we'll keep it in whatever. Yeah, let's forget about the minus for now. Make things a little... Oh, okay, we'll keep it in whatever. Minus 1 over 2 sigma squared. Mu squared minus 2 mu naught plus mu naught squared minus 1 over 2 sigma squared. Sum xi squared minus 2 xi mu plus mu squared. And now let's collect together. What can we want to collect the mu squareds. So let's get all those guys together. We're going to have minus 1 over 2 sigma squared minus 1 over 2 sigma squared. And this is a sum over n things, so it's n times mu squared. Wait, is that what I want? This times mu squared. Yeah, this is n here. Right. Times mu squared. Okay. Right? Yeah, that's right. And then we're going to have the mu's. So let's pull together all the mu's. So this is going to be mu naught over 2 sigma naught squared times it's going to be that plus, we multiply this. Oh wait, not the two cancels, right? 2 cancels there. Here the 2 cancels also, and we're going to get the sum. So it's 1 over sigma squared sum of the xi's times mu. Times that. Okay. And then we get some other terms, and it's just going to be constant. So I'll just put c for whatever that constant is. It doesn't depend on mu. All right. And I think we're not going to care about that. So now let's think about, we want to get it in this form here, right? So let's pull this guy out. We're going to get mu squared, and then we're going to have, maybe I should give that a name. Well, we'll keep it like that for now. Mu squared plus this divided by that. If we factor it out of both of these, gosh, this is getting kind of messy, isn't it? Divide by this guy okay, and that's times mu. And now we need to oh, I guess let's pull the 2 out. I think that's going to make life a little easier. So pull the 2 out here. Then we want oh, and maybe the minus also. Let's make the minus. Yeah, that's going to be good. So put the minus out. And now we want this thing squared. So let's clean this up a little bit too here to make things look similar. So that's going to be minus 1/2 times that. Okay, so this part's the same as this, and now we just want to add the square of this. So let me just call that whole thing, I don't know, let's call that alpha for now. Oh, actually, let's call it mu, or let's call it m. I think that's going to be our m. Yeah, it is. Okay, so now, oh, and we also have to, since we added this thing, we also need to subtract off some stuff. But whatever we subtract off is going to be a constant because, you know, it's just involving this times something over here. So we'll just get some new constant like that. Okay, so now we can factor this guy and get it in that form that we were hoping for. So we get this times mu minus m, right? This was what we called m squared plus some constant. Oh, and I guess this is m also, right? Or no, that's m times m was the whole thing. Yeah. Okay, now let's see. Okay, running out of time here. We'll finish this up in another video. We're almost there.